This conference will now be recorded.
Hello everyone. So last day we have ended with pH of hydrolysis of different types of salt. That is salt made of strong acid, strong base, then weak acid, weak base, and the other combinations. That is strong acid, weak base, and weak acid, strong base. Okay, so all these combinations we have seen. Now problems based on that we will solve first, but after that the topics that we are going to discuss in today's class is buffer solution, buffer action, pH of buffer and buffer capacity, and if still we have time we can also discuss solubility equilibria of sparingly soluble salts. So we'll start with this problem. So the problem is there are total 4 options, and you can see some mixtures of HCl and NaOH of different concentration. So following solutions are prepared mixing different volumes of NaOH and HCl. So NaOH and HCl, these two, that is acid and base, it is common in all the options, but their amount and molarity, that is different. So we have to find that pH of which one of them will be equal to 1. Now when we are saying that pH is equal to 1, that means what will be the molarity? So it will be negative logarithm of H plus concentration, that is actually equal to 1. That means it is minus 1 if I am putting here positive sign. Now if it is true, then the concentration of H plus, that will be 10 to the power minus 1. That means here molarity is 0.1. Now we have to find in which of the solution molarity will be 0.1. So that will be the answer. So the first solution here, what we will do, we will multiply the volume in ml with the molarity so that we can get number of millimoles of HCl. So 60 if you multiply, it will be 6 millimole of HCl, and 40 multiplied by 1 by 10, it will be 4 millimole of NaOH. Now this reaction is 1:1. That this reaction means the reaction between HCl and NaOH. So it will produce NaCl and water. So 1 mole of H2O, that will, 1 mole of HCl, that will always react with 1 mole of NaOH, and it will produce 1 mole of NaCl. Now here we have 6 millimole HCl and 4 millimole NaOH. That means here all the NaOH will be consumed, but 2 millimole HCl, that will remain excess, right? Now the second one, similar way, it will be 5.5 millimole of HCl and 4.5 millimole of NaOH. Again, all NaOH will be consumed and some extra amount of HCl will be there, which is 1 millimole, right? Now in the third case, it is 75 divided by 5. So it is basically 15 millimole. And 25 divided by 5, it is 5 millimole. That means again NaOH is consumed, 10 millimole extra HCl there. And the last one, it is 100 by 10, 100 by 10. That means it will produce neutral solution. So this option cannot be the correct option. Now among these three, we have to find in which case the molarity is 0.1, because that should be the answer. So 2 millimole means what? In terms of moles, you have to multiply each one of them by 10 to the power minus 3. So it will be 0.002. So 2 into 10 to the power minus 3. Now this cannot be the molarity. Then the next one, it will be 10 to the power minus 3. And this one is, it is basically 0.01 moles. Now this number of moles is basically present in total volume. Basically total volume in each case, if you see, it is always 100 ml. So this number of moles that is present in 100 ml, but we need the number of moles in 1000 ml. So 1000 ml, that means 1 liter, that should contain 10 times high, that means 0.1 number of moles present in 1000 ml or 1 liter. So this is according to the definition of molarity. This is actually the molarity which is matching with this. That means option C. From this we are getting acidic solution, but not just acidic. It is not enough because all these three are basically acidic. But we have to find that option where the acidity is such that pH is equal to 1, and pH 1 means molarity is 0.1. So just calculating number of millimoles not enough. Once you are done with the calculation of millimoles, next you have to convert it to number of moles. Now this number of moles basically present in 100 ml. All these cases it is total volume 100 ml. So if it is for 100 ml, so for 1000 ml it is 10 times high. So that is why it is now 0.1, and this is actually according to the definition of molarity. This is the molarity value 0.1. So this should be the correct option. Option C. Okay. Next problem. Now next problem is related to hydrolysis. Remember we have seen some formulas in the last class for hydrolysis of different types of combination of acid and base. So here we have weak acid HA and weak base BOH. So we have to find what is the pH of their salt. The salt is AB. The reaction is between HA and BOH, and they are producing the salt AB and water. So pKa value for this acid is given, for the base is also given, both are weak. So these are the values. Now remember the formula for hydrolysis of salt, which is made from weak acid weak base combination. That formula basically we have to use 7 plus half pKa minus pKb. So just put these two values and you will get your answer. Simple. So this is the formula that we have to use for pH. pH formula for weak acid weak base combination type of salt. Okay. So this is the salt which is produced from weak acid weak base. So that is why this formula we are using. So pK value we are putting, which is 3.2, and pKb value is 3.4. Now in this case, remember when it is weak acid weak base type of combination, then pK, that is pH, final pH, it may be lesser than 7 or greater than 7. Now that depends on the value of pK. So in this case, pK value is lesser than pKb. 3.2 is lesser than 3.4. So that is why ultimately it will be lesser than 7. But if it is reverse, then this part will give you some positive value. So something will be added to 7. So it will always be greater than 7. So in this case, it is pK is lesser. So that is the reason pH value that is lesser than 7, 6.9, and this option should be the correct option B. So among these three basically we have to choose. But if you look carefully, without solving, that is without putting the values of pK, pKb in this formula also you can solve this problem. How? As you can, when you will read the question, you can understand that pK is lesser than pKb. So obviously the value will be something close to 7 but lesser than this. But it is not so less. Remember, when it is weak acid weak base combination salt, it will be more or less between 6 to 8 pH range. It is not so, it cannot be so acidic, right? So this is obviously not correct option. Now among these three, as it is slightly lesser than 7, so this is not correct. 7 is almost, that is exact neutral. This is also not correct. Only one option is left, so which is 6.9. So even without putting values of pK, pKb in this formula, if you are in hurry, you can also solve this problem. Fine. Next question is same type, that is pKb value of dimethylamine. Dimethylamine is Me2NH. This is weak base. This is secondary amine. pK of acetic acid CH3COOH. So this is also weak. So we have weak base. pKb, pK values are given respectively at T Kelvin. The correct option for the pH of dimethyl ammonium acetate solution. So when you are combining these two, the salt that you will get, that is actually dimethyl ammonium acetate. So this is the salt, CH3CO in Me2, dimethyl ammonium acetate. Okay, basically if you put the H here, that is with nitrogen, if you put H, then it will be positive and it will be negative like this, right? If you remove it, then there will be no charge over nitrogen. So this is the salt, which is a combination of Me2NH and CH3COOH. Now under this condition, we have to find pH of dimethyl ammonium acetate. Now here 25 degree is not mentioned, it is mentioned TK. And as we will be using this formula, and in this formula, this 7 last day we have seen it is basically coming from pKw by 2. Now pKw 14 when we consider only when it is 25 degree. So 14 by 2 is 7. But here it is mentioned T Kelvin, exact value is not given. But though it is true that with increase in temperature, there is change in the value of Kw, product of water. But it is not so drastically changed. It is slightly, there is slight increase. So we can ignore that. There will be no problem because the question is framed in such a way. So simply use the same formula as you have used in the previous problem. So pH will be again 7 plus half pKa minus pKb. So pKa value is given 4.77. Now in this case you can see pKa value is greater than pKb. So obviously it will be some slightly greater than 7. Slightly greater than 7 means only this option is left, because this is very high, it will not be so high, it is almost close to 9. This will not be so high. Obviously it is suggested that you use this formula, then only choose the correct option. But even without that also, if we have less time in hand, then also we can choose the correct option as T. So here this part is giving some positive value, so it will be added to 7, which is 0.05, sorry 0.75, which will be added to 7. So this is the correct option. Okay. Arrange the following solutions in the decreasing order of POH. Now this type of question, be very careful. Normally our tendency is it is a very common error we make, that it is clearly mentioned decreasing order of POH, but by default normally we tend to do it in terms of pH, because that is the convention mostly we follow. But be very careful, it is in terms of POH, it is not pH. Okay, so we have to focus on hydroxide ion concentration for all these 4 solutions. So the first solution is 0.01 molar hydrochloric acid, then 0.01 molar NaOH. Then we have in the third option sodium acetate. Now this is not salt, this is salt, it is not acid or base. Then again we have salt, right? Now according decreasing pH, that means if you look at the options B, A, B or A, the first value that is giving highest pH. Now highest pH, highest POH. So when we know, when we talk about pH, when it is lesser than 7, it is towards acidic side, and higher than greater than 7, it is towards basic side. But when you are talking about POH, now obviously it is reverse. So when we are talking about POH, lesser is the value, more basic it will be, higher is the value of pH, more it will be acidic. That is, now it will be completely opposite. Okay. So one by one we will see the first solution, which is 0.01 molar HCl. So molarity of hydrochloric acid is given. So obviously you can calculate the hydroxide ion concentration. Basically first you will calculate H plus, because it is acidic solution. Once you know the H plus, you can calculate pH. Once you know the pH, you can also calculate POH, right? So see, 0.01 molar HCl, that means here H plus molarity is 10 to the power minus 2. So in the formula of pH, you have to put minus log H plus concentration. So minus 2, 10 to the power minus 2, there is a minus sign, so it will be 2. So once you know the pH value, you can calculate the pOH value, which is 12. Now, as I have said that pOH, when it is very high value, that means it is very acidic. And acidic, obviously, you will get the highest pOH value from this solution, because it is the only solution in these four options A, B, C, D. It is the only solution where you can get maximum acidity, because it is only HCl. The other combinations, there is no HCl, right? Not combination, I mean other three component given, there is no acid, so maximum pOH you can expect here. Then for the second one, which is basically basic solution, so in this case pOH, now it will be very low value. Just in case of acidic solution, pH is low, so now it is basic solution, so pOH will be low. Now directly here HO minus concentration is given, which is again 10 to the power minus 2, so directly you can put it here. So this will be the minimum value, see, isn't it? Then what about C? So when it is C, 0.01 molar CH3COONA. Now we, as it is a salt, so we have to consider hydrolysis because it is dilute solution. So hydrolysis we have to consider. Now when it is hydrolysis, look at the salt. What type it is? It is basically combination of acetic acid, which is weak acid, and NaOH, which is strong base. So when we have weak acid strong base type of combination salt, then what formula we use? We use the formula for pH, which is 7 plus half pKa plus half log C. So here half is common. Within bracket we have pKa plus half log C. This is basically log C. C means what? It is the concentration of the salt, which is 0.01. So put here half pKa, even if pKa of acetic, pKa of what? pKa of acetic acid. Even if it is not given, then also you can understand pKa value, it will be something positive. And log 0.01, it is 10 to the power minus 2. So this value, there is something minus 2. But obviously pKa value, it will be greater than 2. And for acetic acid, it is very common. Frequently it will be used. It is basically something 4 point something. Okay, so it is near around 4. So 4 minus 2, it is basically something positive. So it will be greater than 7. So pH, if it is greater than 7, so pOH, it will be slightly lesser than 7. But you can understand, you cannot expect the pOH value to be as low as like this, because it is directly basic solution. And when it is a salt, which is weak acid strong base type of combination, then also it is near about 7. That is, for pH it is slightly lesser than 7, but as we are slightly greater than 7 because it is strong base. Remember, when we have discussed hydrolysis of this type of combination of salt, we have seen pH value is slightly lesser than, greater than 7. So obviously for pOH it will be slightly lesser than 7, but it is not so less like 2. So even without doing calculation, even if pK value, exact value not given in the question, then also you can understand from this type of salt, pOH cannot be so low as you are getting from direct base alkali solution, which is NaOH. So even if we do not do full calculation, we can understand this will give you minimum value, that is component B. And what about the last one? The last one is basically NaCl. It is weak acid, strong base combination, that is NaOH HCl combination. And we know when we have this type of salt, it is always close to 7. So pH is 7, pOH is also 7, right? So here maximum we are getting maximum pOH that we are getting for A. After A, the next value is basically D, then it is C, and then it is B, right? So option 4, that should be the correct option. But I will always suggest that in this type of problem, rather than spending time on calculation, directly also you can choose it. Because when we are talking about pOH, and even if you have problem in doing pOH calculation, First, you can do the calculation in terms of pH. So maximum pH, suppose the problem is given in terms of pH. So maximum pH, it will be for what? Obviously, it will be for NaOH, maximum pH, right? Because it is basic. So maximum will be for B. Now after that, the next value, that will be for what? It will be for C, because it is weak acid strong base combination. So it will be slightly lesser than 7. So next pH, that will be for C. Then it will be for this neutral, because this will give you lowest pH. So it will be at last. So it will be B, C, D, and then now reverse this B, C, D, A, which is basically A, D, C, B. So this is another way which will obviously take less time. If you do full calculation, it will take more time, though it is still suggested, but still you can apply this type of trick, that first do the calculation in terms of pH and then just reverse it, you will get the correct option, which is option 4, or directly you can also do in terms of pH. Okay. So the topics that we are going to discuss today after solving these 4 problems is buffer solution. So what is buffer solution? Buffer solution is consisting of a mixture of either weak acid or its conjugate base, because whenever we have any acid, suppose we have acid, its conjugate base is A minus. Similarly, when we have any weak base, suppose we have weak base B, then its conjugate acid is BH plus. So this type of combination, not just any acid, it has to be weak acid and its conjugate base. Similarly, it has to be weak base and its conjugate acid. So when you have this type of combination, any of these two, then that solution will be called buffer solution. Now, what is the purpose of making buffer solution? Gradually we will see, but first you have to understand what it is. So two types. One is acidic buffer, where you will use the combination of weak acid. This is weak acid plus its conjugate base. This combination. Another one is basic buffer. Obviously it is pH greater than 7. So in this case it is B and its conjugate acid, which is pH plus. This combination we are going to use. It is weak base. Weak base must be. You cannot take strong base NaOH or strong acid HCl. It has to be weak acid, weak base. So basic buffer is weak base and its conjugate acid. That means salt of this base. So see, we have here example NH4OH, which is our B, and NH4Cl. So here we have this ion present. So ion should be present. You can also, here I have written B, you can also consider it like BOH. And the corresponding salt, suppose it is Bx. So now the format is matching with this. So it depends on how you are expressing the base. If it is ammonia type of base, normally we express it in B. But if it is carrying some OH, it is better you express it, that is the general formula, as BOH. And this is the salt. So here common ion must be present, which is NH4 plus, which is also present here. Okay. So this is the salt and this is the base. Similarly, keeping the base same, you can also take another salt, NH4NO3, which is basically coming from ammonium hydroxide and HNO3. When you combine this acid and base, you get the salt ammonium nitrate. Similarly, NH4Cl you will get from ammonium hydroxide and AC, right? So these two are examples of basic buffer. So NH4OH, this type of weak base you have to take, not any strong base. Then we have acidic buffer. So in acidic buffer, you have to take some weak acid like acetic acid, salt of this acid with strong base. Okay. So remember, the salt that you are taking, normally it is with the strong base. Similarly, here also you have seen salt of this base with some strong base. Sorry. Yes. strong acid. So which strong acid salt we have taken? The salt is made from HCl and HNO3, right? Similarly, salt of this acid with strong base. Which base here it is used? It is NaOH. You can also use HCN NaCN combination. HCN is the acid, and we have taken the sodium salt. Again, this salt is made from HCN and strong base NaOH. You can take formic acid, which is another weak acid, organic acid obviously, and the corresponding sodium salt or potassium salt. So it is generated from NaOH, or potassium salt means it is generated from KOH. So these are the examples of acidic buffer. Characteristic of buffer solution. It has definite pH value. Now what it means definite pH value? When you have this specific combination. So this is one combination, then another combination. So each combination there is some specific pH value. Its pH value doesn't change on keeping for a long time. So if you make this solution and you keep it in a bottle and you can preserve it, it will not change with time. Slight change may be there, but it is not something drastic. The pH value doesn't change on dilution also. So this is another important feature, right? And the fourth point, this is the most important feature that must be present in any buffer solution. So what is the feature? The pH value doesn't change even with the addition of small amount of strong acid or strong base. So this is the most important characteristic of buffer, and this statement is actually the purpose of making buffer. So sometimes we need buffer solution. Suppose some particular reaction you want to do in a maintaining a fixed pH, then you have to use this type of buffer solution, where if there is slight amount of strong acid by chance added or base is added, suppose the reaction that you are doing there, then you have to use some reagent which is very small amount, obviously small amount of strong acid or strong base you have to use as catalyst. So it will not create any problem if you are doing the reaction in buffer solution. The pH will still be maintained. Okay, so it doesn't change even with the addition of small amount of strong acid or strong base. So sometimes in chemistry we need some solution, that is suppose we are doing some particular work where pH should be maintained, so then we have to use buffer solution. So that is the purpose of making buffer solution. We can work at a particular pH value. Buffer action. So this particular property of the solution, that is which property? To resist the change in its pH value even on addition of small amount of strong acid or strong base. Remember, it should be strong. If you are adding very large amount, obviously it will not be able to maintain the pH, but if it is small amount, then it can resist the change in pH, and this resistance power, that is actually known as buffer action. To resist changes in its pH on addition of acid or base, the buffer solution should contain both acidic as well as basic part. So how it is resisting this type of pH change? When you are adding small amount of strong acid or you are adding small amount of strong base, how you are doing, it is doing this, I mean to say how it is doing this particular action. So what is the reason behind that? So it means when you are adding some strong acid, suppose you are adding very small amount of strong acid, there must be some basic component in the pH which can capture this excess acid that you have added. Similarly, when you have added some excess base, then there must be some acidic component in the buffer solution which can nullify the effect of the base that you have added. Okay, so that is why here it is mentioned that buffer solution should contain both acidic as well as basic component so that it can neutralize the effect of the acid or bases that we have added from outside. Right, now we will see how it is doing. That is, we have seen two examples. One is the acidic buffer, another one is basic buffer. So first we'll see, if you have some acidic buffer like acetic acid sodium acetate combination, then how it is showing this buffer action, that we will see. But before that we have to understand the two that is the salt and weak acid that you have taken, how they are dissociating in the aqueous medium. So acetic acid is weak acid. So we will use equilibrium sign. In the left hand side we have undissociated acetic acid, right hand side we have dissociated form, and we know it is weak. So very small percentage of it will be in the dissociated form. So it is mentioned here slight ionization, and you are using equilibrium sign. But when we are talking about salt, we know it is always irrespective of the type of salt, it is always complete ionization. We are using single headed arrow. So it will mostly be in the right hand side state. That is, you will get all the molecules, they will be in dissociated state, right? Now, under this condition, when you are adding, suppose you are adding small amount of strong acid. Now what will happen? As we have mentioned in the second point, there is a acidic component, there is a basic component. So when you are adding acid, the basic component is basically this acetate ion. So as it is fully dissociated, you have high concentration of acetate ion. This acetate ion will combine with this H plus and it will produce undissociated acetic acid. Okay, so in this way, this excess H plus, that is the effect of this excess H plus, that is nullified by the acetate ion which is already present in the buffer. Similarly, if you add small amount of strong base like sodium hydroxide, now the acidic component that is present in the solution. So here we have taken which acidic component? We have taken acetic acid, undissociated acetic acid. Now you can say why I have not taken H plus, because that is also acidic component. But see, H plus amount, it will not be very high because acetic acid is dissociated form is very less. So you can take H plus, but you can say that H plus will consume this HO minus, and as the equilibrium according to Le-Chatelier, it will shift more towards left to right. That logic is also fine, but you can also put here the acetic acid. That is because I have written here undissociated acetic acid because the amount of it is high. Just like in the previous case, it is acetate ion that is taken because its amount is high in the medium, in the buffer solution. So we have taken undissociated acetic acid, which will act as acid. It will consume this HO minus, it will produce more acetate ion, and as the amount of acetic acid is decreasing, then also according to Le-Chatelier, more of acetate ion will be produced. Okay. So in this way, this is the acidic component, basic component which is consuming excess H plus. This is the acidic component which is consuming this excess HO minus. In this way, it is showing the buffer action. Okay. Now, mechanism of buffer action if it is basic buffer. So here we have taken this basic buffer. First, we will see how these two compounds, how they are dissociating. So as NH4OH is weak base is dissociated from to ammonium ion and HO minus, it is slight. We are using equilibrium sign. But salt, it is always fully dissociated. So we are using single headed arrow. We will get all the molecules in the form of ammonium ion and Cl minus. That is complete ionization for the salt molecule. Now when you are adding extra HCl small amount, there must be some basic component which will consume this extra H plus. So here basic component we have taken the undissociated ammonium hydroxide. You can also take HO minus. So when HO minus will consume H plus, more of NH4OH, it will be in more dissociated. That is also fine. You can also take NH4OH because that is present in excess amount. It is light ionization, so mostly in the medium you have NH4OH, and that will react fast with H plus, and it will, in this way, it will nullify the effect of extra H plus. It is NH4 single positive charge, and water will be produced. Similarly, if you add excess NaOH small amount, then there this extra hydroxide ion must be consumed by the acidic component that is present in the medium. Now, the acidic component is ammonium ion because this ammonium ion is generated from the salt NH4Cl and it will nullify the effect of excess HO minus. It will produce undissociated NH4OH. Okay, so these are the mechanism of buffer action for acidic buffer and basic buffer. Now, one more information. This is not very common buffer, but for our knowledge, we should know this. So in the previous slide, we have seen there are basically two types of buffer. The type 1 is acidic and type 2 is basic buffer. We have not mentioned any third category. Now, sometime in some books, textbooks, you can also find there is a third category, but this is not very common, but still we will have some that is introductory idea about it. So look at this molecule. Here we have not taken any, that is two component. In the previous two examples, it is a mixture of weak acid and its conjugate base or weak base and its conjugate acid. But now we have taken a single molecule. Now this is obviously a salt. And look at this salt. It is made of what? It is made of weak acid and weak base. Now this is not very common type of buffer, but still you can see some examples in some textbooks, so that is why I have mentioned it. Acetic acid NH4OH, it is producing the salt ammonium acetate, and directly this molecule, sometimes it can also show buffer action. So ammonium acetate, as it is a salt, so obviously there will be complete dissociation. So single-headed arrow, it will produce these two ions. Now if extra acids are added, suppose HCl, then there is a basic component. This one is basic component, this one is acidic component. So the basic component will consume H plus, and when extra HO minus added, that is NaOH or KOH, then this is the acidic component which will consume this. So this molecule also sometimes it can behave as buffer, but mostly when we talk about types of buffer, you will see mainly two types, acidic buffer and basic buffer. Now the important question is how to measure pH of a buffer solution. And for measurement of pH of a buffer solution, there is a particular equation which we use for calculation of pH, only for buffer obviously, is known as Henderson-Hasselbalch equation. Okay, so what is this equation, how we can derive it, that we will see now. So first here we have taken weak acid HA, and suppose we have a salt Ma. It may be acetic acid and it's sodium salt. So M is metal, mostly alkali metal. Now when it is acid, obviously its reaction with water, you can directly write HA producing H plus A minus, that is also fine, or you can use water molecule. In that case it will be hydronium ion, not H plus. Both are fine. So it is light ionization because it is weak acid, but as Ma is salt, there will be complete ionization. So in the medium, you have now these metals. Sorry, it is plus charge here. You have this metal cation. It may be Na plus K plus. You have A minus, which is basically the conjugate base generated from HA, and you have hydronium ion. So these three components you have, right? But we are mostly interested in these two, not M plus. Next, this is actually the final formula, that is the equation that we are going to use, but we will also see how we can derive it. So these two formulas you have to keep it in mind, because using these equations again and again you will solve problems that are based on buffer solution. That is problems where you have to calculate pH of buffer or pOH of buffer. So when it is weak acid conjugate base combination, that means you have taken HA and its salt with some strong base, that is acetic acid, sodium acetate. Then first you have to write pK value of this acid, then log, In the numerator, you have to write the concentration of conjugate base. That means concentration of A minus. So if it is sodium acetate, it will be acetate ion concentration. And in the denominator, you have to write the acetic acid combination, or in general, if I write it is H. Sometimes you will see that in some books, negative sign is used in place of positive sign. So in that case, you just have to reverse this. Then it will be concentration of HA first divided by concentration of A minus. But if it is positive sign, first A minus divided by HA. Similarly, when it is basic buffer, so you will get now instead of pH, it will be POH. Then pKb value you have to put, which is for the base, that is the weak base. Suppose I have taken NH4OH and NH4Cl. So here conjugate acid, you have to put the concentration of NH4 plus, and in the weak base portion, you have to put the concentration of NH4OH. And pKb, that will be pKb for NH4OH, that is the weak base. So this is the final formula, but we will see how we can derive it. So for this equation, if you consider Ka, that is ionization constant of Ha, it is concentration of hydronium ion, concentration of A minus divided by undissociated Ha, right? Now, next, as the salt, which is Ma, that is completely dissociated, right? The second equation, it is complete dissociation. That means in place of concentration of A minus, you can put the value of concentration of the salt. So in place of concentration of A minus, you can put the concentration of the salt, because these two are basically same. Whatever concentration of A minus you are getting in the buffer, that is basically coming from Ma. You can also say that it is also coming from Ha, but Ha is very weak and Ma is complete dissociation. So mostly the concentration of A minus, significant contribution is coming from the salt Ma. So that is why you can put in place of A minus concentration, you can directly put the concentration of salt. And as Ha, it is basically the acid. So the concentration of acid, that we will put here. So the same equation, if we are writing in this way, see what change we have done. In place of A minus, here it is written salt. In place of Ha, it is written acid. So it is basically same thing, right? Now if it is so, then H3O plus concentration, now it will be Ka into acid divided by salt. So we have arranged the equation in this way. Why? Because now we will take negative log here, which will give us pH. Then negative log Ka, which will give you pK. Then negative log of acid by salt, and if you remove the negative, it will be salt by acid. Okay, so see, when you have taken log, first we have taken positive log, so it is like this, log acid by salt. Then negative sign, when you put it, it will be pK and this will be pH, and negative sign is there, so it is acid by salt. But if you make it positive, it will be salt by acid, which is here. See, here positive sign is present, so it is conjugate base by acid or salt by acid. So this is the final formula we are getting. In a similar way, you can also derive the second equation. So these two formulas we will use when we will solve the problem related to buffer solution. One more important term we have to know related to buffer, which is known as buffer capacity. So what is the definition of buffer capacity? It is basically quantitatively defined as the number of moles of acid or base. That is, remember in buffer solution what we say, when we add excess, small amount of excess acid or base, then there is no change in pH. So we are talking about that acid and base. It is basically the number of acid and bases, number of moles of acid and bases that you are adding externally to 1 liter solution of any buffer. That is the amount, that is the moles that is required for 1 liter buffer to change the pH by unity. So suppose The pH is, there is a particular value. Suppose I am saying the pH is 7. Now you are adding externally some excess acid or base in such a way so that now the pH value is increased by 1 unit. That means now it is 8. So for this increase, the number of moles of acid that is required or number of moles of base that is required, that value is buffer capacity. This is the definition. 1 liter solution of buffer. So buffer capacity, you can write it in this way: number of moles of acid or base added to 1 liter of buffer divided by change in pH. That means when it is change in pH is 1, this value in the numerator, that will directly give you buffer capacity, and that is the definition. Now buffer capacity, it will be maximum when salt and acid, these two concentrations same. Remember the formula Henderson-Hasselbalch, pH is equal to pKa plus log of what we have seen, salt divided by acid. Now salt and acid, when these two are same, these two same means what? This part, it will be log 1. So now pH is equal to pK. So when this part is coming as 0, then buffer capacity is basically maximum, and that is true for acidic buffer. Similarly, when salt is equal to base, that is POH equal to pKb, log of salt by base. Ratio is changed. In that case, pH will be pKb when these two are same. So buffer capacity is maximum. That is, it cannot show buffer capacity more than this, right? So this is the definition. And important point: greater the buffer capacity, larger is its capacity to resist the change in pH value. So suppose we have buffer solution 1, buffer solution 2. In the first case, the buffer capacity value, and in the second case there is different buffer capacity value. So in these two solution, you can compare when buffer capacity is high. So that means its resistance power to change the pH value, that is also high. Okay. That means for unit change of pH, we have to add more acid and more base. So its tolerance limit is high. That is why greater the buffer capacity, larger is the resistance for the change in pH value. Here we have which will make basic buffer. Now basic buffer means what? It must be combination of weak base and its salt, right, with some strong acid. So the first one is 50 ml 0.1 molar NaOH and acetic acid. That means there is a chance of formation of sodium acetate, and weak acid is already there. So it will make, that is, it is asking which will make basic buffer. So it will make something, though exact number of millimoles we have to calculate. But remember, it is combination of NaOH and acetic acid. Then we have acetic acid and NaOH again with different values of ml and molarity, but it is still NaOH and acetic acid. In the third option, we have weak base and strong acid. So now there is a chance you can get some excess weak base if it depends on millimoles, whether you will have excess NH4OH and there is some NH4Cl. If it is so, then option 3 can be correct answer. And the last one, here both are strong, so this cannot be correct option, right? And also there is just by looking at this problem, it seems as if option 3 should be the correct option. But we will solve it and we'll see whether it is, the base is correct or not, because basic buffer means it is weak base and its salt. So the first one, see, acetic acid NaOH. So here what we have done, volume in 20 ml, 25, and this is the molarity. When you multiply it, you get number of millimoles of acid, and 50 0.1, 50 0.1, you are getting 5 millimoles. That means this is the limiting reagent. All the NaOH will be consumed and there will be some extra amount. Sorry, this is limiting 2.5. So all the acetic acid will be consumed. This will remain extra sodium hydroxide and there will be some sodium acetate. So we have salt, but we have strong base and this cannot be buffered. So even without doing calculation, you can say this cannot give you the correct answer. Then the second one, the same type of calculation, multiply the volume in ml with molarity, you get number of millimoles 10, 10. So both are same. So there will be only salt, which is weak acid, weak base type of salt. But this is not basic buffer, right? And see here, if you look at the value, then also you can understand it will be, that is direct neutralization will be there, right? Now option 3, 100 ml 0.1, that means 10 millimole HCl and 20 millimole NH4OH. That means excess reagent will remain this. HCl is limiting. Some extra NH4OH is there and there is also salt. So remaining, what is remaining? We have salt, we have weak base. So option 3, as we have already guessed, this is actually giving you the correct option. So you don't have to do full calculation, though I am showing it because if you are interested, obviously full calculation we should see, but even without doing calculation, we can choose the correct answer. And the last one, it is 10 millimole, 10 millimole. So it is neutralization, even if it is not 10 millimole, 10 millimole, then also as both are strong, how we can get buffer, right? So the calculation is showing that option 3 correct option, but I will suggest that even without doing full calculation, just by looking at it, because it is asking basic buffer, and basic buffer means weak base must be present, and from option 1 and 2 you cannot get weak base, you have strong base, NaOH, NaOH in both cases. So even if it is present something extra, then also it cannot make basic buffer. So why calculation is required? Okay, so option 3 is the correct option. Okay, 20 ml 0.1 molar H2SO4 solution. So H2SO4, it is added to 30 ml 0.2 molar NH4OH. Now see, in H2SO4 two replaceable hydrogens there, so it should be 1:2. It will produce salt, ammonium sulfate and water. So this is 1:2. This is the ratio. Now we have 20 ml 0.1. If you multiply it, it will be 2 millimole, and NH4OH it is 30 into 0.2. 30 into 0.2 means it should be 6 millimole. Now for each mole of H2SO4, 2 NH4OH moles required. So 2 millimoles, it will be fully consumed after reaction. It will remain 0. So for 2 millimoles, required amount of NH4OH is 4. So excess amount will be 6 minus 4, which is 2 millimole. Now from 2 millimole of H2SO4, and these two are 1:1. So obviously here also 2 millimole NH4 ammonium sulfate will be there. Now it is asking pH of the resultant mixture. So in the final mixture, what we have? We have NH4OH and we have ammonium sulfate. That means we have weak base and salt with some strong acid. And this is 2. This is also 2. Both are 2. Sorry. One thing you have to notice, there is a chance of error. It is 2 millimole. But we have to understand not just salt concentration, we have to understand how many NH4 plus ions are present. So it is 2 millimole, but number of NH4 plus for each millimole it is 2. So it will be basically 4 millimole. Don't be very careful. Now we will use Henderson-Hasselbalch equation, which is POH, PKB, log of NH4 plus divided by NH4 OH. So pKb value is given 4.7 and this is log 4 by 2 and log 2 is basically 0.3, so it will be 4.7 plus 0.3, it is, but it is asking pH. 5 will not be answered and not also in options, so pH will be 14 minus 4. So option C is the correct option. So here if you make this mistake, if you make both these same, answer will be wrong. Though it is true that even if you make it 0, you will get answer 4.7, right? So when you subtract it from 14, so it will be you will get wrong option. Okay, so be very careful. It is not 2 millimole. 2 millimole is basically NH ammonium sulfate direct concentration, but we have to understand what is the number of NH4 plus ion. So per mole of this salt we have 2 moles of ammonium. So that is why we have written here 4 millimole, and you can do the calculation in terms of millimole. You don't have to convert it to moles because it is ratio. So millimole, even if you convert to moles, it doesn't matter. After all, it is a ratio. So that is why directly number of millimoles you can put. That is, even if you don't have to put the concentration. So that is why we have not considered that this number of moles present in which volume, because that will giving you molarity. But we have not used molarity because it is a ratio. Volume is same for both. So even if you do the full calculation for molarity, that is actually not required. Directly you can put the millimoles when you are using Henderson-Hasselbalch equation. Okay, so we will end the session here. Thank you for listening.